So now next step, what we will do is we will use the SystemVerilog constructs and really create this test bench. And this test bench will be like a simplified version, and there can be optimizations that can be done or the enhancements that can be done, and those will be the exercise, right? So a base structure of the FIFO test bench we will go through as a part of this session, and that code will be provided to you, and there will be exercise to improvise certain things. And the idea is that you have to explore this code pattern, right, and understand at least few simple patterns of using the language to build the test bench. That is the whole idea, right? Because it will take a while for you to create right patterns by yourself. So and before you are able to do that, you need to know few patterns of how to do things, and then you over a period of time you evolve and you can create your own patterns or improvise the current patterns. So but before you do that, you should become familiar and more comfortable with at least few patterns. That is the idea. So this exercise, as a part of this exercise, once we go through this session, you should again go through the code base and make sure that you are becoming comfortable, and you should be able to do some changes and understand how this works. This is very important because most of the cases, as a part of your job, I mean, few of you guys would find probably the opportunities to start off in a new project, but many of you will find opportunities where something is already built and you have to take that, understand that particular code base, and then start doing some enhancements, right? So when you have to do that, what needs to happen is how the test bench structures, how the test bench is generally structured, and if I need to add a new test, how should I do it? If I need to add a new functional coverage, how do I need to do it? If I need to fix a bug in scoreboard, where should I look at it? So that type of pattern should be there in your mind so that you can navigate to those parts of code, and then you are able to focus in a specific area and get to the part where you need to do something. So that is very important. So not only the fact that you should be able to build new test benches, but more important is that you should be able to take existing test benches and you should be able to understand. And not only this code, you should explore and find out other codes from different GitHub repositories and take a look at it, right? So the learning to read code and understand, and how you should read it is that you should have this structure of test bench that has been taught to you, that should be there in the back of your mind. At any point of time you should be able to map it. Okay, where are the generators, where are these translators, where is the scoreboard, where are the drivers, where are the monitors? So you should be able to ask those questions and look for those answers. That is the whole idea of this exercise. And the second point is that as I have repeated at the beginning of this session, you have not yet learned the SystemVerilog, but the idea is that you should be able to look at the use cases, and many of these constructs, as we explain, you will be able to understand what it is doing. You may not be able to understand the construct in all its details, but to the extent that is required to solve the current problem, you will definitely be able to understand it. And what we will do is, now once this is done, you will have at least one pattern that is set in your mind as to how the language gets used, and that will help you when we start going deeper into each of these constructs as to where does it fit in, right? Like for example, classes, where does they fit in, threads, where do they fit in, and then interfaces, clocking blocks, how do they work, right? And how do, like, what are the different ways we can use the procedural code. So various things will be sort of set in your mind, and then when we go deeper into each of those constructs, you will know where this construct is going to get utilized. So it's sort of a little bit of a reverse order, and it sort of ties in with our initial idea that you should be ready to do verification every day, right? So that is the idea. So let's now get into the actual implementation. So step one of building test benches, as we have been already seeing, is connecting DUT to the test bench, right? And that's done by instancing the DUT and connecting all its ports, and which could be further either monitored or driven by your test bench. So in the Verilog world, what we were doing was we were instantiating. So it's a Verilog world instantiation I'm showing before we show how the same is done in the SystemVerilog world. So we are instancing the DUT, and then we are declaring this bunch of wires and edges to hook it up. So all general rule of thumb is all your input ports will be connected to reg variable, and all your outputs will be connected to wire for monitoring. And what you can notice over here is that although these set of signals that we are connecting are sort of related, like for example the write and then the FIFO full and D in, right? So this is a write port related signal or a push interface related signals. But when we see the discrete wires, there is no relation that's coming out, right? So because of this, what happens is if I want to instance multiple of FIFO DUTs, I will have to instance them separately, and in terms of the connectivity also there is no reusability, right? So, and it's all like every connection is a separate connection and every wire is a discrete wire, and hence it's also error prone, right? And if we look at closely when we say we are doing connection as to what it contains bunch of signals, and then we have a sense of direction if we view it from either a DUT or a test bench. That is, for example, the FIFO full is an output from the DUT side, whereas as it's an input to the test bench side. So there is some sort of a direction, and there's a clocking information, right? So in the current case, all of these signals are synchronous signals synchronized to this FIFO clock, right? So this is what essentially is contained when we talk about the connection between the DUT and the test bench. Now let's see if we were to do the same thing in SystemVerilog, how it is done. So in SystemVerilog, they have introduced this new construct called interface construct, and interface is nothing but is just a named bundle of wires or variables, right? So it's just a name given to it, and so you declare the set of wires in it, and then what we do is this interface, once we have declared a bunch of wires in it, has two things. So one is something called a Modport. So Modport allows you a view of these signals, right? So an interface is just a container of wires, and when I look at the interface, I can access any wire in any direction. Like for example, the data in is of the type logic, so I could either be driving or I could be reading it in, right? So there is no sense of direction, and the sense of direction is provided through these Modports. So Modport are views to these wires as to whether do we look at a particular wire as an input, output, or in-out is decided by your Modport. And then there is a second dimension that's called as a clocking block, right? So clocking block allows you to build a synchronous interface. That is, once I have defined a set of signals in a clocking block, and when I drive those signal, right, so they are automatically driven on the clocking event specified in the clocking block. For example, if I look at this push CB, which is a push clocking block, the clocking event is a passage of clock, and I can also specify this sampling delays. So these sampling delays are essentially representing right, like when you have a FIFO, you have a setup and you have a hold time type of a considerations, right? And that hold time consideration comes from your output delay, right? So now those can also be specified over here as to like when a particular signal needs to be sampled with respect to a clock, and when it needs to be driven with respect to like a clock to output delay that it needs to be driven can also be specified as a part of the clocking block, and all the related signals can be listed over here. So we have a push clocking block and we have a pop clocking block, and both of them are driven by the same clock. We can specify the direction of the signals that we have listed in the interface either within the clocking block or explicitly within the Modport as well. And this Modport can be attached to a clocking block. So in this case, what we have done is we have defined the clocking blocks, and within the clocking block, while we are defining the signals, we are also defining the direction of them, and hence we are attaching the clocking block to Modport, right? So in summary, we have created a set of signals, and those signals direction can be direction or the view of the signals view meaning the direction and the clocking information is controlled through the mod ports, and then mod ports are built using the clocking blocks, right? And the interface as a construct can also take in it can also contain tasks and functions as well. We will look at it in a more detail, but the most important part is, although the interface itself is a static entity, but we can create a virtual interface as well. Using this static interface, we can create the virtual interface, and those virtual interfaces can be passed to different tasks, functions, and this is what forms the connection between the static module world to the dynamic based class world that exists in the SystemVerilog. And we can also, so once we have created virtual interfaces, virtual interface is just like a variable, and as long as the types are matched, so for example, I could be having a particular FIFO virtual interface, and I could have multiple FIFOs instance. Any FIFO's interface could be passed to any virtual interface, right? So that flexibility comes in that, and that is what helps build the dynamic connection to the dynamic simulation world of classes. Okay, I understand that things might be feeling slightly tricky at this point, but just try to pay attention and understand from big picture point of view at this point of time. We will get into the details of each of these constructs. So just to sort of, like from the previous slide, you just understand that there exists so anytime a DUT needs to be connected to the test bench in SystemVerilog, it is done through interface constructs. So that's first point, is to remember that. Second point, there exists a concept of mod port, right? And mod port provides the views to interface to help you set the directions. That's the second point. Then there exists a clocking block that helps you provide information about when a signal needs to be driven and when it needs to be sampled. So okay, just get this point. I think these 3 points are fairly simple. Just hold them on the back of your mind. And now let's see. So here, now what we are doing is we are creating, again, we have a test bench top. It's a module, doesn't have any ports. And we are going to add any test bench top is a container for your DUT as well as your test bench, and the connection between the DUT and test bench. Those are the 3 things that we will be doing in the test bench top. So we have instanced this DUT, and now if you see compared to the previous slide, instead of connecting to the individual wires, I am connecting them to the wires present or the variables present inside the interface. Now, what could happen is that if I could write a SystemVerilog DUT top, and if I write a SystemVerilog DUT top, and then I can use the interface itself as a port. And if I do that, this connection becomes even more simpler. But just to do it gradually, I have not done it over here. This is still a Verilog DUT top, and what we have done is we have instanced this FIFO interface as a interface. We have created an instance of this interface. So the FIFO interface as a construct, as I had mentioned, is very similar to module. So we have instanced the FIFO interface, and we are using the variables present inside that FIFO interface to hook it up to our design, right? And then we have additionally externally generated the clock and the reset, and those we are passing it as the input to our interface, right? So, and keep that in mind that interface is not a port. Interface is basically all your connections. So it's abstracting the connections that are taking place, and to those connections you can now define the views, because connections by default do not have direction or do not have any clocking inform. They are just bunch of connectors. Right now, using mod ports and clocking blocks, you define the like the clocking information as well as a direction, right? So keep that point in mind. Now the important point that's happening over here is that we are creating another instance over here. This is the test bench top instance. Typically in SystemVerilog world, we use another construct called a program block. Okay, so program block is again a module equivalent. The difference between a program block and the module at this point of time at a very high level is related to scheduling, right? So the the components or the modules that are or any of the code that is present inside the module is scheduled before in a time step than the program block, right? So now how this helps is that the first DUT gets a chance to do something and then the test bench acts upon that, and this helps prevent the race that can exist. Now what are those races? Don't worry about it at this point of time. We will look into it when we go into the scheduling semantics, but just understand the fact that what is a module for a TB top, right, is a program block for the test bench in SystemVerilog. So from this code snippet, what you need to keep in mind is, one is you have the one is the test bench top is still a module, and second is you instance the DUT and you instance two different things over here. Instead of just a bunch of wires, we are creating a SystemVerilog interface instance, and then we are instancing a SystemVerilog program top, which is the top for your which is the container for all your test bench code. And the reason for using the program block is in terms of scheduling, it is scheduled such that it prevents the races that can happen between test bench and RTL. So this is all that you understand from this piece of code. Okay, so I hope you are with me so far. So what we have been able to do so far is we created an interface through which we were able to connect the test bench and the DUT at the test bench top. Now what we are going to do is we are going to start implementing the the interface layer in our test bench, the layered model. If you remember, we are going to start implementing like a push driver, right? How do we activate? Now I understand that you might not be knowing where this push driver is sitting and how it is being connected to the interface. So we will come to that point. Just hold that thought. What we will look at initially now is, what I wanted to show was that now that we have created an instance of interface and passed that interface to the program block, and we have through that program block it will come to your push driver. How does the push driver use that particular interface and drives the signals? That's what I wanted to show you in this particular slide. So this is the task. This task is actually a part of push driver. Briefly, I will show you more details about the push driver. For now, just focus on how it is driving using the interface, right? So only focus on that part. So if you look at it over here, so we have a while loop, right? A do while loop. And what we are doing is in the do while loop, we are waiting on this at FIFO push interface underscore v dot push cb, right? So this push cb is a representation of the clocking event that we had defined it in the interface, right? Now there we had defined it as a passage of the clock. Now the advantage of specifying it in this way is that if at all I change the clocking event to some other clock, or if I change the clocking event to, let's say, negage of clock, I don't have to go and change it everywhere, right? So I can just change it over there, and whenever I refer to my clocking block, clocking event, then it will implicitly imply the clocking event that is associated with the clocking block. So that way it provides you that advantage and abstraction from which clock are you using and which clocking event are you using for the driving is abstracted out, right? So I'm waiting for that, and every time an event takes place on the clocking block, I am looking at FIFO push interface underscore v, and the clocking block that is present within the FIFO interface forms the hierarchy. So I'm looking at that particular clocking block and I'm checking if it is full is asserted, right? So I'm checking if the full is asserted, and if the full is asserted, I will keep looping over here, because if the full is asserted, I don't want to do the push, right? So I don't want to write into the FIFO, that will be overflow, right? Or the data that I push will get lost. So I'll keep waiting for it, and then once the FIFO full is deasserted, at the beginning if I look at it, my FIFO full will not be asserted. So immediately I'll be able to come out of this loop. So the next step I will do is I will refer to this FIFO push interface. I'll use the clocking block, and then I'll say data in is equal to I am picking up the data from a transaction that is coming in. So if you look at this push task, I am passing in a FIFO transaction. I know you might be wondering what is this FIFO transaction. We will come to it. Don't worry about it. We'll come to this point. So I am taking the data present from that FIFO transaction and putting it out on the data in interface signal. And this interface, the way I am driving it within this particular driver is through a virtual interface. So I will show you that detail when we go further. And then I am asserting the write enable signal. So similar way I am referring to push interface underscore v, that's your virtual interface handle for the push interface Modport, and then I'm using the clocking block hierarchy and write enable. Now whenever I write it through this clocking block, what it means is these signals will be driven on the clocking event that is specified in this clocking block. Okay, we'll see that in the waveform. And then what I do is after driving these, I'm waiting for one clocking event of the clocking block, and I'm incrementing push count in the FIFO state. So what is this FIFO state? We will see this. But this FIFO state incrementing will help activate the pop driver. We will be able to see that later. And then I'm deasserting my write enable signal to 0. So this is what I'm doing. Now, how does this translate in terms of waveform? So you have the clock and the reset is released over here. And after the reset is released, I see that the full is deasserted. So because the full is deasserted, it will immediately come out of this do while loop. And then whatever the data that was coming in through this FIFO transaction is being assigned. So think of this FIFO transaction is like I would, if I had multiple arguments, instead of passing them as a multiple arguments, I am encapsulating all of them through this FIFO transaction. And this is a class. So we will look at it in the next slide. What is it? And then that data is being driven and the write enable is asserted on the rising edge of the clock. And we are waiting for one clocking block event, which will be the next POSIT, and I am deasserting it. And that deassertion is happening after one unit time delay that we had specified in the clocking block, right? So this is the way now the write enable gets asserted to the FIFO. So this is how we are driving the FIFO interface, right? So I hope this gives you an idea that how we use the interface and how we extract it from the transaction and how we are able to drive it on the FIFO write interface. We will next see now what we are going to find out is a few more things that we have not the few things that we have not talked about over here is one is what is this FIFO transaction, we have not looked at it, and second is how this FIFO interface underscore v, the virtual interface that came into this driver, we have not looked at it, and where is this task sitting, right, and which is the container for this task, that also we have not seen it. So what we will do is first we will see what is the container for this particular class and where are all these properties, like the virtual interface property is declared within that class, right? So we will look at that next. So I am repeating few things frequently over here because we are kind of dealing with all the new things. So far what we have been able to do is we saw an interface, we saw a Modport which was a view to your signals, we saw a clocking block which provided the information about when the signal is going to be sampled and when it is going to be driven. This is the first part, and then we saw testbench top, and testbench top we saw instance of interface because interface as a construct behaves more or less similar to a module, and then we saw instance of DUT and we saw instance of program block which contained all your testbench code, right? And this interface that we connected to the DUT, we also passed it to the program block, right? And then we saw, without seeing where the driver was located, we saw how the write or a push interface of FIFO was driven using the clocking block present inside the interface. That is what we saw so far, right? So now what we are going to do is we are going to expand the view a little bit further and look at the task that we saw in the previous slide where we were driving. Where is it located, right? So now this is the class. This is the class for the FIFO push driver, right? So now SystemVerilog has this new data type called class, and class groups your data and code together, right? And all your test bench components are modeled using classes. And one difference that you can look at from class to module is class is dynamic, right? So the module is static. So what that means is once you have compiled and started a simulation, if a module is instanced, it is going to be present throughout the simulation, right? But a class can be instanced and it can be destroyed, right? So during the course of simulation, a class can be instanced and can be destroyed, whereas a module, once instance, cannot be destroyed in the simulation. This is a very important point that you should remember. Now, why I am talking about that point is here there comes one statement called active components have threads, right? So what the active component means is, so some of the classes also stay throughout the duration of the simulation, and some of the classes are created and destroyed, right? So there are, although classes can be destroyed, some classes are kept throughout the duration of simulation, and some classes are created and they are destroyed as soon as the usage of that particular class is over, right? So if you remember, we looked at FIFO transaction, right? We will look into a little bit more detail further. So FIFO transaction is an class instance that gets created again and again, right? So if you want to issue 20 FIFO operations, then 20 times FIFO transaction gets created, and as soon as it is driven out or as soon as we have received a pop, it gets destroyed. We will look at it in more close detail, but the driver is not such, right? So the driver, once created in an your test bench environment, stays throughout the duration of the simulation, right? So stays throughout the duration of your test. The driver instance of the class will remain active, right? So that is why a generator is an active component, and it will have its own thread, right? In the SystemVerilog, we have seen fork based launching of procedural code. So it will have one thread because it has independent existence. It can receive FIFO transactions and it can process and drive. So it has to have that independent existence, it will have internally a thread, and we will look at it a little bit more further detail. Now, we had seen that in the test bench we had generators. We had a push generator that was connecting to your push driver, right? So now the information from your generator to your driver is done with the help of mailbox, right? So mailbox is a construct present in the SystemVerilog that helps communication between two processes. A generator is an independent process. When I say process, you will have internally a forked thread. So you have a generator process and you have the driver process, right? And then between those two threads which are present in two different classes, the communication takes place with the help of a mailbox, right? And mailbox helps you pass. So what happens is generator creates this FIFO transactions, and the FIFO transactions are put in a mailbox, right? And you can imagine a mailbox, right? Like we put the letters in, right? So we put in the letter and that gets delivered to the recipient, right? In the recipient in this case is your push driver, right? And what the push driver does is it takes the virtual interface of the FIFO interface that we have created, virtual because we are doing it in the class which are dynamic in nature. So it takes the virtual interface and it drives it out. It drives the information that it has received through the FIFO transaction on the virtual interface with the help of set of tasks or functions, right? So that is what it is doing. So if we look at it over here, so we have this interface virtual instance of the FIFO interface, and we are using the Modport type push interface. And when we use this, automatically the clocking block within that becomes accessible, and we have giving the name of instance over here, and we have declared a mailbox. Mailbox is also a keyword, although it's not highlighted over here, but the mailbox is a keyword, and then we are giving the name to the mailbox, generator to push driver, right? And then we have one more class instance called FIFO state, and we have created an instance of that particular class. We will talk a little bit further as to what this class does, and every class will have something called constructor, and it's always annotated, I mean, which it's always referred with the function new, right? So it's called function new, and to this we are passing the virtual interface, the mailbox that we intend to connect, and the FIFO state, right? And then this new gets invoked whenever I create an instance of this class, right? So that is what happens. Now, where do we instance the FIFO push driver, and from where are we passing these parameters? We will look at it further in the next few slides, right? So hold that thought. So, and additionally we have function called init, which will initialize your push driver, and then you have a task called run. We will see what happens. This is the place where your threads gets launched, and the main thing I want you guys to pay attention is push in FIFO, right? This is the function that we saw in the previous slide, that this is the function that was taking this FIFO transaction, and it was using this virtual interface, and it was driving it out on the actual interface signals, right? So it was doing the write or the push to the FIFO DUT, right? And then we have the main. So this main and run are kind of like a set of common functions that we would need as a part of any active component. This is nothing like, this is not a methodology or anything, but it's just a the best known practices that you launch the threads in a particular function and provide one entry point to every class, so that the component or the class that's instancing this particular class can call this entry function, right? So that is the whole idea. So next what we will look at is that we will find out more about where is this class getting instanced, how is this information getting passed, and how the class like how are the threads present in this class and how they get launched, right? So we will find that out further. So we are still continuing to understand this driving push interface, right? So what we have been able to understand is, we saw this like push in FIFO function as to what it does. That's the first step that we saw, right? So what it does was, what it did was, it took this FIFO transaction and it had access to the virtual interface, and through that virtual interface it had access to the virtual interface, and what it did was is extracted the information to be driven on the interface from this FIFO transaction. It assigned those values to the virtual interface, and it was able to create a push, or it followed the push protocol, like it waited till the full was deasserted, and then it put the data on the data bus and asserted the write enable that we have already seen, right? And then second point, we saw that this particular task is present in class, and class is a dynamic entity, and how it is different from the module we have already seen, right? And we saw that in the driver class we have this function called main, right? So now, so far, why are we looking at main is because we wanted to see when is this push in FIFO task getting called, right? And how is it getting the information to be driven out, right? So we had already seen that in this class, FIFO push driver class, we had a virtual interface which is connecting to the DUT side, right? So we have two sides to this driver. There's one side where we are connecting to the DUT, and there's another side which will connect towards the generator. So if you remember that layered architecture, the bottom there was a DUT, and on the top layer is the layer which there was a driver that was present, and on the top of the driver we had the generator, right? So the bottom part is connecting to the DUT using the virtual interface, and the top part is connecting to the generator using the mailbox that we had declared, and the name of the mailbox was gen to push driver, and the mailbox is a construct provided in the SystemVerilog, and it is meant for interprocess communication. Now what happens is that in the generator it will create a FIFO transaction, which is again another class, and it will be put into the mailbox, and it will be put into the mailbox using the put inbuilt method provided in the mailbox. We will look at it more detail when we go into the generator in the next slide. But here, let's say the transaction has been put. Now what we do is we peek. So peek is a another inbuilt function of the mailbox. What it does is it does not remove the transaction from the mailbox. It just gives you a copy, right? A copy of that particular. So if I had, so it's not removing, it's just giving you a copy of the transaction from the mailbox. And but what happens is that since the copy is not removed, let's say, so what happens is I generated a transaction in the generator and I put it into the mailbox, and if the mailbox is sized to a value 1, as soon as I put it, the generator gets blocked because the size is 1, right? So it is occupied. So now I cannot put any more into this mailbox because the size of mailbox is only 1, right? So now put that in. Now and let's say my push driver was waiting on that particular mailbox. So through this mailbox, my generator and the driver are connected and is of size 1, right? So I have put it. Now as soon as I put, my generator is blocked, and while my push driver was waiting for something, and that wait was happening through this call for peak, right? So and in the peak, what happened was it got a copy of the transaction to drive, but still the transaction itself is not removed from the mailbox. Since it is not removed from the mailbox, now the generator will not be able to generate another transaction. And why we have done this is because this transaction, I could have done a get over here, right? Instead of peak, I could have done a get over here. If I had done a get, then the generator would have gotten unblocked to generate the next one before I have actually had a chance to drive it out on the interface. So this concept you have to pay attention and understand, because this is something that's similar going to remain and develop further when we go to the UVM, and the same concepts are created in a more advanced form called transaction level modeling ports, or the TLM ports will come into the picture, but the concept remains same. So what you do is you take a copy and you still, till you have processed it or till you have actually driven it out on the interface, you don't take it out of your port or take it out of your communication channel, which in this case happens to be a mailbox, right? And then you call push in FIFO, right? And we know what happens in push in FIFO, and I am passing this transaction, and this transaction will be driven out on that virtual interface. And after we drive it out, right, that we waited for the full to be not asserted, and we put the data and we asserted the write enable, we have done all of those steps. After doing all those steps, the task will come out, right, that it has finished its job and that has consumed time. And now what we do is we take out that particular transaction out of this mailbox. So we are taking that out, and once we take that out, the generator gets now unblocked to generate a next transaction. So typically what we do is peak, process and get is the loop in which we do. Peak, get a copy, and then process. It could be any type of processing that you are doing while you are consuming the time. You actually process that particular thing, and only after processing and when it is completed, you take it out of your communication channel, so that the next the transaction that needs to be processed can be sent to you. So far we have seen like how the push driver is operating, and how it is able to push the transaction on the virtual interface using the mod port and the clocking block present within that particular mod port. Now let's complete this entire the thread of activities or the line of activities. So let's look at how we are generating. So as we talked about, most of the test bench components are modeled using the class. So even generator is modeled using a class and thread, right? So it's an active component. The thread aspect of each of the class, we have not looked into it so far, so we'll look into it a little later. Now in the push generator, we can see we have a mailbox, right? So if you remember, the communication between your generator, the driver, the push driver and the push generator is through the mailbox, right? So this particular mailbox. So we have declared this mailbox, and we have the FIFO state class instance and a FIFO config class instance. What are these classes? We will see it later. Hold on to that thought. And we have the constructor, FIFO, the function new, and this new gets called whenever we create the gen push class instance. Creating class instance is in a way similar to, you have to create, like just declaring a class doesn't do anything. It's very similar to if I just declare a module separately, it doesn't do anything, right? We have to instance that module somewhere, unless it's a top module, right? So other modules you have to instance it somewhere to make them operational. Similarly, if you just declare a class, it's not going to do anything. It has to be instanced. So when the class gets instanced, the function new gets called, and while instancing the class, we can, like, while we instance a module, we are able to pass the ports to the module. Similarly, when we instance the class, the arguments that are defined in this function new can be passed to the class, right? So we will look at it in the later slides, but we are passing the config, we are passing the state. So config and state in a way are global objects. If you remember from the testbench architecture, your config and state are global objects which bias or which model or which help shape the traffic that is generated from these generators, right? And what we are doing, so we are creating this variable we have declared these variables within the class. We are assigning whatever we have received as arguments to the variables present inside this particular class. And what we will do is we'll look at what the main thread of the push class does, right? The generator push does, right? So what we have done, we have declared this handle. So when we talk about the class, there are two things. One, we need to declare a handle, and then we need to call a new on that handle to instance that particular object, right? So FIFO transaction is a class, and with that particular class name we have declared a handle. And then what we are doing is, if you see, we are using the config, right? So in the config there is another variable called FIFO operation count, and we are saying for these many counts generate the FIFO transactions, right? So that's what we are doing it in the generator, right? So we are, see, if you here, we have declared the FIFO transaction handle, and for that FIFO transaction handle we are calling new, right? And whenever the new is called in this format, the new function of the FIFO transaction class would get invoked, right? So whatever the functionality that is present within the new function of this particular class would get called when I call new, right? And then if you see, I am calling another function called randomize, right? So we will look at it a little bit further. So what it does is, whatever the variables that are declared as rand inside the FIFO transaction class would get randomized, right? And default, they can take a random values based on the type of data, and if and you can add additional constraints wherein you can define how the values that it can take can be limited. So that can be done. So we will look at it when we look at the FIFO transaction class. We will understand how we have declared the random variables, and those random variables that we had declared with a rand keyword will get a random value depending upon the data type and the constraints that are defined on that particular variable, right? And the randomization can pass or fail, because randomization can have at times dependencies, and if the dependencies are not satisfied, the randomization might fail. So it's always important to check if the randomization is successful, and if the randomization is successful, then we can take that particular class and consider the variables that we had declared as rand have the legal values. If not, then we will have to terminate the simulation or take some action, all right? So here we are checking that if it's failed, then we indicate it is failed. And what we are saying is, we are saying the transaction type should be push. And then once we have created, if the randomization is successful, then what we are doing is we are taking that transaction and putting it into this gen to push driver mailbox, right? And as you know, this mailbox connects to our our push driver, right? And the push driver is capable of taking this particular transaction through its peak, process and get to be able to drive it out on the FIFO push interface, right? So that is what is going to happen. So in the generator, what we were able to do was, we declared the handle for the FIFO transaction, we created an object and we call the randomize on that particular object, which will randomize the variables of the type rand, or only of the type rand, which are present within that particular class. And we can specify additional inline constraints over here, and we said the type of transaction should be pushed, and we took that transaction and put it into the mailbox. And once I put it into the mailbox, the driver will be able to extract this particular transaction and drive it out on the FIFO push interface. So this is the overall flow. So we were able to see how it was generated and how the generated transaction was sent through the mailbox to the driver, and in the driver we were able to take it, process it and send it. Now one can think, why are we doing all this, right? So why are we creating so much of complexity in the whole process? The idea is that we want to reuse some of these components, right? So sometimes I could attach now the driver to a different type of a generator. Right now that is possible only if the functionalities are cleanly segregated out, right? And in the complex projects, as well as in a case where you are developing a SOC type of a chip where you have multiple IPs, there is a lot of reuse possible, and that reuse is only possible if we are like cleanly cutting out the component, and one component does one type of a functionality, the generator only generates, the driver drives. So when we define this type of a clean functionality, functional boundaries, then the reusability becomes better and they are easy to maintain, and then the debuggability improves. So this is the reason why we do divide the functionality into the different components. So far we have been following how the push interface of the FIFO was being driven. We looked at the driver and we looked at the generator, and we looked at the fact that the driver and the generator were connected using the mailbox, right? So the mailbox was connecting between them, and through mailbox they communicated in the form of FIFO transactions. Now what we will do is we'll look at what is a FIFO transaction, right? So a FIFO transaction is also a class, okay? And what the point to note over here is, so this FIFO transaction as a class is only used in the form of an object, right? It's not an active component. It is not going to contain any internal thread. So unlike your push generator as well as driver, they remained active throughout the duration of test, but the FIFO transaction instances will not remain active throughout the duration of test, but multiple copies of FIFO transaction will get created and destroyed as a part of your test, right? So like we had put a repeat loop in the generator, so like 10 copies, if I had specified count of 10, then 10 copies of this FIFO transaction will get created and they will get destroyed. So once it has been driven out and nobody is holding the object copy, then that particular class instance automatically gets destroyed. Like unlike in C++ or C, where you have to release the object, the SystemVerilog does automatic garbage collection. That is, as soon as nobody is utilizing any objects of a particular class, it automatically gets garbage collected, right? And the one new thing to note over here is that if you have different constants, right? Like for example, we wanted to create different transaction types. So we have push, pop, let's say push when full, pop when full. These are the different type of transactions we want to create. Then these constants we can give specific names, and then that is what is done with the help of this enum. All right. And when we study the data types of the SystemVerilog, we'll look into a little bit more details of it, right? But what we are able to do is we are just giving the names to various constant values that we can use, and how it helps is it makes the code more readable. So we are creating a variable, we are declaring a variable called FIFO transaction type, and that's of the type FIFO transaction type _t, and this type _t is of the type enum. And the key point to note over here is all of these variables we are prefixing with this keyword called rand. And the way it works is, if I have some variables which are also called as properties within the class declared with the keyword called rand, and whenever I call randomize function on any objects of this particular class, then depending on the data type and the constraints, they will take any random value allowed by the subset, of the values that this particular variable can take, right? Like for example, data, right? So data is 7 down to 0 over here, so it can take any 256 values because we have not put any constraints, right? So it can take any value from 00 to FF. It will pick any one value, right? Whereas your FIFO transaction type will pick any value from these 4 values unless there is an additional constraint. So if you remember in the gen push, we were saying there was an inline constraints that we were putting. The constraints can be put either in the class or as a part of the randomize call inline, right? So we had put an inline constraint saying that this type should take a value equal to push, right? Now for the data, we are not putting any constraint, so it can take any value between 00 to FFF. And the delay between the operation, we are putting some constraints, and what it will do is it will take like less than 8, so it will take only value that is less than 8, right? Although the delay can take much different ways, a 4 down to 0, so it can take up to 32, but it's not going to take 32 because we have put a constraint over here. It is always going to take only less than 8, all right? And then we can provide some functionalities in this class, object class. Like we are providing functionality called compare, wherein we can compare one instance of this FIFO transaction object with another instance, right? So I am passing another instance and it is comparing the value of data that is present within this to the value of data present in the argument that I have passed, right? And if they match, it will return 1. If they don't match, it will return 0. Now just keep this function in your mind. This is a function that will be utilized while we are doing the scoreboard, right? So in the scoreboard, what we will do is we will take the actual and expected, and with respect to one, we will pass the other and ask to compare, right? And it will do the comparison and tell us whether it's matching. So this is how the transaction classes are created. At a very basic, you can understand that like in the Verilog, we were passing all the variable information that we wanted it to be driven on the interface in the form of arguments to a function or a task, and then we were independently randomizing it, right? Using the urandom or urandom range, we were independently randomizing it. Whereas in the SystemVerilog world, what we can do is there are two things that we are doing differently. The first thing is we are putting all those related variables together in a class construct, and we are prefixing them with a rand keyword, and then we can add constraints, right? And then what will happen is instead of those variables getting individually randomized in Verilog, now they are collectively getting randomized at one place, and then whatever the relationship that we require to randomize, we can define it within this class, and this class is now passed as a single entity or as an argument through either the interprocess communication mechanisms or as an argument to the task and functions to another component that is present within the test bench, right? So now this completes the overall picture that we have now defined a driver, we have now defined a generator, and we have a mailbox for communication between them, and we have this transaction that goes through the mailbox and passed between your generator and a driver, and how this particular transaction is getting randomized, right? So because we have been so far talking about how do we do constrained random verification, right? So now we are able to put the constraint and we are able to randomize the data part of it, and that randomized data is being driven out on the interface, right? So that is what we have been able to see. So to an extent, we have seen in essence how this overall process takes place. When we say constrained random verification, how that happens, right? So we are able to see it through this simple example. So transaction object has multiple use cases within the test bench, right? So we have seen that currently this FIFO transaction, we were using it between the gen push and the gen driver, right? The same FIFO transaction will also be used between like a gen pop and a pop driver. It's going to use the same thing, and the monitors that collect the push interface transactions as well as pop interface transactions are going to use the same FIFO transaction, right? So you can see that this transaction type can take various values, and based on the transaction type it will be interpreted appropriately. Although I understand that the transaction type could be little bit of a superfluous in this case, but it has put in place to make that point that a common transaction could be used for different purposes, right? And then different components within your test bench could use the same transaction, and the fields required for all the types of communication are made a part of a transaction, and depending on the transaction type, the transmitting and the receiving entity, the two entities that are communicating with each other, know which fields to utilize, right? And even your coverage models are going to use the same transaction to do the coverage collection, right? So like the monitors, whatever the transactions that they are collecting are sent to both the scoreboard as well as to the coverage models, and the same transaction type is utilized even for the coverage model. Right now, so one question that might arise in our mind is that, like, what type of information should be part of a transaction? So typically I have seen that sometimes people tend to put all signals that are present in the interface as part of transaction, though that is not required, because fundamentally what we are trying to do is we are trying to rise the level of abstraction, right? That is, we are creating a high level transaction that can be driven on a signal level interface. So there is some level, the driver will have to do the job of driving the interface, right? And it has to follow that protocol. So not all values that are driven out on the signal level information need to be passed through the transaction type of an object. Okay, so that is a point that we need to keep in mind. And as we have already called out, throughout simulation, multiple times the transaction gets created and destroyed, right? And we have seen that we can also put the utility functions like the one that we have put in, like compare, which gets used in the scoreboard, and the constraints limit that we were specifying over here can potentially use the config and the state object that we had created. Those are the global objects here. Of course, we have not used them, but we can also use them inside the transaction object to bias the stimulus that gets generated, right? So in the constraints, we can use the state and the config objects and say whatever config dot some property, or like for example, now the delay, right? We could put the max and min delays inside a configuration object, and then we can say the delay between operations is greater than like the FIFO config dot min delay and less than FIFO config dot max delay, right? So we can utilize that in the transaction object. So transaction and the component that processes transaction, right, which typically we used to call it as transactor in some of the older methodologies, is a very key concept that we need to understand, that all the parameters that needs to be changed, that can be varied, that can take different values from a high level stimulus perspective, are put in a transaction and they are randomized, and that randomized transaction is sent to another component. That component could either translate it into another thing, or it could do that and process it like a driver, which is the final destination, and it could drive it out on the duty interface. But all the components in a object oriented environment based test bench always talk through the transaction, right? And we have talked about what should the transaction contain, right? So I hope that is clear. So we have looked at the usage of an config object inside the, for example, the gen push. We were using the config object to figure out the number of push operations that it needs to generate. So now let's look at what does this contain. So the configuration is also modeled as a class, right? We can see class FIFO config, and configuration typically contains information that is randomized once per simulation, right? So if you compare config with the transaction, right, transaction was randomized for every operation, right? So but whereas the configuration would be randomized only once per test. Okay, so that's a very important distinction. And configuration is also it doesn't contain, it's not an active component. That what that means, it's not going to contain thread, but it's created only once during the test and randomized only once, right? So that's the nature of the configuration object. And this configuration object can contain any microarchitecture specific variables that needs to be randomized, or any specification defined variables that needs to be randomized. All the variables that needs to be randomized once per simulation, and can be put into your configuration object, right? And then a test is expected to randomize the configuration object that decides in which configuration of the design we can run the particular test. So we can put even the user defined parameters, like for example here we are randomizing the number of FIFO operations, right? So number of FIFO operations that we are generating is not actually part of any specification, it is something that we have defined, but there can be parameters that are defined by specifications, right? And which we can put it in as a part of, like, let's say there could be, I mean here it is not there, but let's say there could be an interrupt enable or disable bit, right? Now we could randomize that particular bit over here, right? Or let's say there is a microarchitecture control indicating what should be the total size of the storage, right? Or which it could be allowing multiple storage size, then that also can be randomized over here, right? So any parameter or a variable that belongs either specification defined or defined by microarchitecture can be randomized over here. And this is a global object, so what happens is this configuration object would be passed to all of your test bench components, because all the stimulus that is generated will be in line with this. So any processing of the information that they do, they will need the configuration object to process it, right? So here for this one we have just declared one rand int unsigned type of an variable for the operation count, and int is again another data type as a scalar data type. We'll look at it more detail when we look at the SystemVerilog data types. And again we have put a constraint over here, and this constraint we are saying it should be the FIFO operation count should be greater than 4 and less than 8. That is what is the constraint we have put. And the constraints that is provided in the class can be overridden, like we know that if we have declared a variable with a rand, the random value, one of the random value between 4 and 8 would be selected when we call dot randomize on this particular class. All right, so and we have provided one utility function called print config, and this is an important point, that for all the transactions you would want to have a print function, so that like as soon as configuration is randomized you want to print it out, or whenever you are processing a particular transaction you want to print it out, and this helps a lot while doing the debugging. All right, so we are looking at different object types that we are using in this particular test bench. We have looked at FIFO transaction, which contained random variables that gets randomized multiple times per operation, and we looked at the configuration object, right? The configuration was a global object that contained random variables that were randomized only once. Now we look at the FIFO state. So FIFO state is also modeled as a class, right? And state type of an object is typically created to track the DUT state as well as test bench state, right? You can track the overall state, and any state information that you want to track can be present as a part of your state object, right? And the state object is also a global object that's typically passed to all the test bench components, because many times when they need to process something, they could rely on a state, right? Like there could be a coverage model that is processing certain event, and now it needs to know in which state that particular event has happened, to make sure that if some events are expected to happen in different states, then we need to cross it with a state to make sure that we are covering all possible ways, right? But in this particular test bench, what we are using this state is for tracking the number of push and pop, right? So as soon as we push, we increment the push count from the gen push, and the same count is looked at by the pop generator, and then if the push count is not matching the pop count, it will generate more pops, and then the pop count gets incremented appropriately, right? And we have also provided an additional control for pausing the push and pausing the pop, right? And whenever it is set, we should be pausing the generators, right? And this type of pausing could potentially be helpful for creating corner cases where I want to keep pushing for certain number back to back before starting the pop, right? So if I want to create such scenarios, then this push and pop, the pause type of a control will be very helpful. And if you note, there are no random variables, right? Because we are not going to randomize the state variable, not randomize the state class, right? So not every class needs to be randomized, not everything need to contain random. So state is one such global object which doesn't contain any random variables and is primarily used for tracking the state, and it's a global object, and it is created once in the test bench, and it stays throughout the duration of the test. And typically a state object also doesn't contain any threads, all right? It doesn't contain, it's just object. Okay, so far I think we have completed the complete loop of push generation, and we saw that we had gen push, and it was using the information from configuration to generate the push, and then that incremented the push count in the state, and then the generated transaction was put in a mailbox. From the mailbox, it was accepted by the driver, and the driver drives that particular transaction on the push interface, right? So we saw that complete cycle and all the components that are involved in that particular processing. The only thing open over there is where did we instantiate those components and how did we connect all of them. That part is still open, we will look at it. So before we get into that part, what we will do is we'll quickly look at how the pop flow is created. And the pop flow, as you will see, will be very similar to the push. And this shows and the reason why I'm showing the pop, gen pop, and the gen like the driver for the pop is to show that some concepts are, the reason why we need to understand these concepts are these patterns are universal, right? And to a large extent you can employ the same pattern meaning the division of functionality between different objects. You can utilize the same type of functional division and implement different type of variety of functionalities, right? And so let's look at it. So this is also a class and it will contain a thread, right? And what we will do is instead of really looking at the complete pop generation mechanism, right, we will look at how the main thread of the pop gen is modeled, because rest of the functionality remains same. So if you see, we have a mailbox which is from gen to pop driver, and we have the FIFO state and the FIFO config, which are the global objects, and all of them are being passed through the constructor and stored within the class variables. We had not looked at the functionality. We will look at the functionality of the main, because main is something that is different for the pop compared to the push, right? So if we look at it over here, we are again declaring a FIFO transaction, and we have one forever loop. So forever is another construct that is provided by the SystemVerilog. You can think of it as equivalent to while one, right? It keeps repeating unless we kill this particular thread or we have some break condition, right? So if we look at it, what it is waiting for is it's doing the push count minus pop count from the state, right? As long as it is not equal to 0, it will wait for that. So which means that as soon as a pop generator is started, it will wait on this particular condition. Wait is another the thread control construct that is provided by the SystemVerilog. So you wait on this particular, so level control based wait, a delay you can say delay mechanism also. So you wait for that, and then once this difference has been created, which means that at least one push has been generated, then we create a new transaction, and you see that we again randomize. So pop randomize doesn't have much of a value. I have done it just to show the uniformity. So you randomize the pop transaction, only value over here is we set the transaction type to pop. So if we have any constraints within the class, that gets overridden with the inline constraints over here, and then we put that particular transaction into gen to pop driver. We put this transaction in that mailbox, and this mailbox would be connected to the pop driver, and pop driver will use this transaction to actually create a read or pop on the pop interface of FIFO. So if we look at the overall class of the pop driver, it's almost similar to the push driver. So it has this virtual interface. Now note that we are actually taking a virtual interface of the type pop, right? So we are taking a we are taking a FIFO interface, and we are using the pop IF mod port that gives the pop interface view of the FIFO interface, right? So we are creating a virtual variable over here. This is actually a variable, it's not a static thing like an interface, it's a virtual interface. Then we have the mailbox, and then we have the state, and all of them are being passed through the constructor. And if you see the functions init, run and main, right? So these are common functions, that common tasks or functions that we had seen even with the gen push. The only different function is pop from FIFO, right? This is the only different function that we are seeing. And let's look at briefly quickly like what does it do, right? So again, this particular mechanism is same. There is a do while loop, and it's now using the pop clocking block, right? Now see, the advantage over here is using the pop clocking block. Now today we are using the same clocking event for both the push and the pop clocking blocks. Now I can easily change the pop clocking block clocking event to a different pop side clock, right? Like a write clock and read clock. Let's say it becomes an asynchronous FIFO. I can easily change it. I don't have to make changes over here in the code, right? It gets automatically adapting from synchronous FIFO test bench. I can make it an asynchronous FIFO test bench without having to make changes in our drivers, right? Although the physical interface characteristics is changing, I'm not making changes to the driver. So that's the advantage that you gain by doing the abstraction. Now what I'm going to do, so once the non-empty, when I find the FIFO to be non-empty, I will assert the read enable. I'll wait for a clocking event of the pop clocking block, and then I will sample the data from the FIFO pop interface, virtual interface, pop clocking block and data out. So it will be sampled just one step before that rising edge of the clock, right? It will be sampled, and that value will be put into the transaction. There's a transaction that we have received in which we are going to put the data that we have collected, and we increment the pop count in the state, and this incrementing the pop count in the state blocks the main thread of this particular pop generator. If you remember previously in the pop generator, we were waiting on difference between the push count and pop count. Since we increment the pop count over here, that generator again gets blocked, right? And then we deassert the read enable, right? So that is the end of popping or reading a transaction from the pop interface. Now you can see that there is a lot of commonality, and the same pattern continues. See, so far, so we have completed the entire push interface flow and the pop interface flow, right? We have completed both of them, but we had not looked at how the threads within them are modeled, right? So now here I want to show how the threads are modeled. So in the run task of each of these drivers, what we are doing is we are creating this forever, and within that forever we are doing fork, and in the Verilog you had already seen fork join, right? In the SystemVerilog, if you notice, there is now a join any, right? A different variation to the fork that has come into play. What does the join any does is that we have launched multiple threads. As soon as one of them finishes, this particular fork block will complete, and the execution will move to the next statement after that particular fork block, right? So that is what the join any does, right? And then so what we are doing over here, in one of the thread that we are waiting for any asynchronous resets, right? And in the another one we are calling the main, right? And what happens in the main you have already seen, right? In the main we were doing peak, process and get steps, right? From the mailbox we were extracting peaking the transaction and either driving it out on push or pop interface, and then we were doing get from the mailbox to ungate the generator to generate the next transaction. That is what we were doing it in the main, right? And so how this helps is that this main will also keep doing forever, it will keep doing that job, and this thread will be blocked, and if at all an asynchronous reset gets asserted, then this will come out of it, and whatever the main thread was doing, it gets aborted, and then it restarts the process, and it starts waiting for the new transactions to come out, right? So that is how the reset handling is done within the each of the driver. Now what we have to note over here is that we have lot of common things, right? So and like we could see that we had the init, we have this thread management, so all this common code we can reuse it, right? And the way we reuse it and how we reuse it is where the UVM comes into play, right? So because there were these type of patterns that people observed again and again, that when we built a good test bench, then these patterns were observed again and again. What they did was they extracted these patterns and then they put them in a different base class libraries, so that every user doesn't have to write them again and again, right? So that's how the UVM started evolving, and we will look at the UVM when we get to those sessions. So we have completed the entire flow for the drivers, right? So now let's look at how we can implement the monitors, right? So monitors are also implemented through the class as active components. They have thread. But before we get into those details, let's look at how exactly the monitoring part is done, right? So this is the main task of the push interface monitor. So if you look at it, we monitor the on every so we can create actually. So what we have done is in the interface we can create another mod port for the monitor itself, right? Because if you look at it in the push interface, we would like the data to go out and the full information to come in to the test bench, and then we want the write enable to go as an output from the test bench, right? So and then that direction would be reversed if the same port was implemented in the DUT. But for the monitor, we want all the signals to be input, right? Monitor will not drive anything. It will only read the information from the interface and capture them in the form of transaction and send it to the other test bench components. So we have created one more mod port in which all the signals will act as only input. And what it does, it waits on the write enable through the clocking block to be asserted, and once it finds that it has been asserted, it creates a new transaction and it samples the data in and the full from the interface, right, and pushes it onto another mailbox. So here we have created one more mailbox, that is from push monitor to the scoreboard, right? And ideally what we would have wanted over here is, now what happens if I do not connect the scoreboard and if I leave this monitor port open, then the transactions will pile up over here and this thread will get blocked. If I have sized the mailbox to be of the size 1, immediately after the first one it will get blocked and it will not work, right? So ideally what we would have wanted was that even if nothing is connected, that gets popped out automatically, and it continues to function, right? That is the way we would have preferred, and such implementation actually exists in the UVM. They have created this concept of analysis port. We will look at it. So currently anyway we have kept the implementation simple, and we are just using the mailbox, and we will connect the scoreboard which will pop it out of this particular mailbox. And the similarly we have the pop interface monitor, which is not very different from the push interface monitor. And also what we would have preferred was that we wanted the monitor transactions to be put into a communication channel, and from that channel ideally we wanted multiple components to be able to snoop information from it. Like we could have a scoreboard or we could have a coverage monitor, all of them to be able to consume the information from the same port, but that type of a built-in data type doesn't exist within the SystemVerilog, right? And that's where UVM has solved it with the help of analysis ports, which addresses these issues that you can connect the output of monitor to like a single output communication channel to multiple components, and all of them can source the same information, and if they are not present, then it won't block the functionality of the monitor. Right, so they have implemented those, and those improvements you will be able to see it when we look into the UVM. So why I am pointing these things out is that you are now able to see how things are becoming slightly better compared to Verilog, and I am pointing out some of the more difficulties that we still have if we were doing it with only system Verilog, which would get addressed when we do the UVM based test benches. UVM based test benches is mainly that you achieve higher level of reusability and more standardized way of building it, because here the tasks and functions that we are defining, we could define any name, right? Like main and run, I could give any name. I mean, this is a name that I have chosen, right? But then someone else may choose different names. So when you use UVM, the same functionality gets standardized, the names of those functions get standardized, and any common code that exists gets standardized, so that everyone will do the things exactly in the same way. So let's look at the class level details. We saw the main functionality of the monitors. Let's look at the class level details. So it's modeled as a class, and as I had already told, it's an active component that will have its own thread. It will have existence throughout the duration of test. So it will be created once and it will stay active throughout the duration of the test, and it is taking in a FIFO interface with a Modport type push monitor interface. So the push monitor interface, as we briefly talked about, it is going to take all input ports, right? So it doesn't need any driving capability, right? And it has this mailbox, and we have the constructor that is defined, which takes the input of the interface and as well as the mailbox. And then we already saw the functionality of push interface monitor task, that how it waits for the write enable to get asserted, and thereon samples the interface and puts it into a transaction and sends that transaction through this mailbox to the scoreboard. And also the monitors not only monitor the interface, but they also look for any protocol violation. So here it is simple, but if you are implementing any AXI or AMBA type of an VIP based monitor, interface based monitor, and then if there is any protocol violation that takes place, the monitor is expected to catch them and flag. For example, here if we did a push on a full condition, then it's expected to catch it. So although there are multiple ways of implementing the checks, but the point is that monitor can also implement checks that are required. Now let's look at the scoreboard. So scoreboard is an end-to-end checker. What that means is, if the data went into the FIFO, did it come out, and did it come out in the correct order, right? That is what is the end-to-end functionality. And the scoreboard is actually basically a model of DUT itself. DUT transfer function is modeled in the scoreboard, and what the idea is, we apply the same inputs that we are applying to the DUT to the scoreboard, which is sort of model of DUT, abstracted model of DUT, and then the output from the DUT are extracted and compared to the scoreboard, because the scoreboard is expected to produce the correct expected data, right? So we take that and do that. And in our case, now what happens is, the both the monitors, they provide these mailboxes, right? Like the push monitor to scoreboard and pop monitor to scoreboard, they are connected to the scoreboard. And if you notice over here, we are using this new data type, this FIFO-Q $, right? This is a new data type which is introduced in the SystemVerilog. It's the aggregated data type. We'll look at it more details when we learn the SystemVerilog data types. This aggregated data type is nothing but a model of FIFO, right? It has push and pop functional built-in functions which ensures the ordered data movement, and we have used the same thing to, this is nothing but the model of DUT, right? A built-in data type that itself can act as a model of DUT. So so we are just taking the virtual interface here for monitoring the reset. That's all. If we generate any intermediate resets, see, generating intermediate resets and handling them across test bench is one of the tricky area. The intermediate dynamic reset generation is an very tricky area, and this test bench also has issues handling them, which some of them we will fix it as part of the exercises, right? So if you look at the the scoreboard is also created only once at the beginning of simulation, and it stays active throughout the duration of the simulation, and it can contain its own threads depending on how you model it. Ideally it should contain a thread. So this is a class, and then we are taking in both of the mailboxes coming from two different push and pop monitors, and those mailboxes we receive it through the constructor, and then we will look at how these functionalities are implemented in the next slide. So if we look at handle push, right, what we are doing over here is that we wait on the push monitor to scoreboard, and we get a transaction from that, and we use the built-in function called pushback, right, whatever we have received, and we push it into this FIFO queue. The FIFO queue behaves exactly as per the DUT, right, we push it inside, and we come to the handle pop. Again, it's forever, we put it in the forever, and we wait on the pop monitor to scoreboard mailbox. Whenever a transaction becomes available in that, we take that transaction out, and we pop a transaction from the FIFO queue. So pop front is a built-in function that is provided by the queue data type in the SystemVerilog, and we pop that particular transaction. So now the order is expected to match, so we get the expected transaction. And if you remember, within the FIFO transaction we had implemented this utility function called compare. So in the from the expected transaction we call compare and pass the actual transaction, right, and then inside the compare function it will check whether the data is matching, and if it is matching, the scoreboard is happy, and if it is not matching, it will flag an error saying that there has been a data mismatch, right. Now briefly let's look at the thread functionality that is present within the scoreboard. So we wait for the reset to get asserted, and what we can do is we can clear any state, right. So if the reset gets asserted, since we abort the current operation, we can clear the state. So in the FIFO queue we were storing all our reference transactions. If we assert the reset, even the DUT will clear all its pointers and reset it back to the quiescent state. So we are also clearing our FIFO queue of any transaction that we had stored, and then this main functionality will get restarted again, and hence things will again work as per the expectation. So the thread, the way we do it is sort of similar to what we have already seen, how we did it in the push and the pop driver. Only the additional thing is we are clearing any internal variables that we are using within the component. We need to clear their state. Okay. So so far I think like one thing that we have accomplished is, one big feat we have accomplished is, we have looked at all the components, right. So two layers of components, right, the low level driver monitor for push and the driver monitor for the pop interface we have looked at. We have looked at how the generate push is created. We have looked at how the generate pop is created. We have looked at the scoreboard, and we have looked at the configuration object, and we have looked at the state object, and we have understood what are the active components, and we have looked briefly at the thread, and we have looked at how the reset, intermediate reset, is handled within each of those threads using the fork concepts, which is very important. And now we are ready to put all of it together, right. So far the only part that is missed is, where were these components present, where were we instantiating the objects for these classes. That is a part that we had not looked at it. So now we will look at that part, right. So typically there is a environment, and environment is also an active component or active object which will contain a thread, right. And environment is the place where all the test bench components are instanced and connected, right. And the only part now remaining after we are able to define the environment is we will have a test object, right? We'll have a test which instances the environment and accomplishes the scenario, right? That's the only part that will be left. So, and any changes that we require for the scenario creation, we can do it with the help of the configuration object, right? And what the environment does is it does the tick include of all the class files that I have not shown over here, but it does a tick include of all class files, or the SystemVerilog provides another construct called packages, right? So packages can, as the name itself suggests, right? So the package is a package, right? So you can put everything together, right? So all the classes you can put it together in a package, and then instead of including the classes individually, you can include the package and all related classes will come in to the target in one shot, right? So that is a way you can use the packages. And so once we have included the packages or the classes that we need, now we have access to them. So we are now declaring a FIFO interface, right? So here if you look at it, we are just declaring a FIFO interface. There is no Modport information, so it's a complete interface that we are getting, but it's a virtual interface. So anything in the class world will be a virtual. It will be like a variable or a reg type, you can think of it like that, right? So whereas the actual interface, in a way, I mean, it's very loose, it's like a wire or a static type of a data, right? So what we will do, we are creating the handles for the global objects, our FIFO config and FIFO state, and we are declaring the handles for all the generators, that is the another layer, and then we are declaring the handles for our drivers and monitors, which is our low level layer. Then the FIFO scoreboard, we are declaring the handle, and we are declaring the handles for this all the mailboxes, right? The mailbox being the built-in data type within the SystemVerilog for interprocess communication. So we are declaring those mailboxes that we are going to do the connection, and then we have the constructor which will receive the FIFO interface on which it needs to operate, and then we have set of functions which are tasks, wherein we build, reset, run and finish, right? So we have these 4 tasks, and what happens is in the build, we create, we like through the new, right? New is our constructor. New is the function through which we create the object for a class handle, right? So we will call the new and we will do the build, and in the run, what we will do is we will launch off the run thread of each of the active components, right? So for all the active components, as you have already seen, they contain a run task in which in the forever loop they were calling their main, and in the main they did whatever their primary functionality, right? So in the environment run, we will call the run task of each of the active components, and in the finish, we will wait to see whether the intended scenario is completed, and as soon as the intended scenario is completed, we can finish the the existence of the environment. So that is what we are going to do it in the FIFO env. Now let's find out further that how each of these gets implemented. So let's say, so this is the constructor for your environment. So we are creating the so we were saying that all the objects are built in the build phase. These are called phases, and the similar type of concept will even come in the UVM. So here we are doing it in a simplified fashion. So we are creating the FIFO config and FIFO state little earlier than build, and the reason being that config, I might have to change it if the test requires it, right? So that is the reason why in order to override it, we are doing the we are creating the config object before then the build. So we will look at an example. When we look at an example, you will be able to understand, right? So now after that, in the build, if you see, we are creating the gen to push driver mailbox, and if you see, the argument value is 1, so it is sized to 1, and then I am creating the gen push, and I am passing this FIFO config object that I've already created, FIFO state, which is another global object that I've already created, and then the gen to push driver mailbox, right? So all these arguments that I have created I'm passing, and if you look at it, so we need to connect this gen push to push driver. Anyway, the interface is common, but if you look at it over here, this is the same mailbox, right? The gen to push driver mailbox that I had instanced over here, I'm passing it to both the gen push as well as to the push driver. So this is how they get connected, right? And then after doing that, I am calling the init so that any internal initializations that are required for the push are completed, and I'm instancing a monitor to scoreboard mailbox, and I am instancing a monitor, and I am passing the corresponding interface, and then I am passing the corresponding mailbox. I am doing the similar process with the pop, and at the end I'm instancing a scoreboard. I'm passing the push monitor to scoreboard mailbox and pop monitor to scoreboard mailbox. So this way, by using these common variables, right, and this with the monitor, right, I am able to connect all these components together, right? So using this I'm able to connect. Of course, this process is again improvised in case of the UVM, so we will see how that does when we get there, but just remember that we are putting some manual effort in being able to do this by ourselves, because we are managing it all by creating the new objects and making sure that the common ones are connected appropriately. So we are doing it. So how this becomes better, we will see it when we go to UVM. So once we have now in the build phase, we have connected everything together, and here in the reset phase, now there is one possibility that we could be controlling the reset generation through the environment, but in this case, for the simplicity, what we have done is in the top level TB top itself, we were generating the reset, if you remember. So it's just waiting for that reset to get deasserted so that it can synchronize the run. So it will wait for this reset to get deasserted, and then in the run, what happens is that every component's thread is started off, right? If you see the run of all of them, we are starting off, we are forking them out so that none of them blocks each other. So although internally they contain the thread themselves, but additionally we are forking them off so that there is, even if some component is not doing a thread internally, it works properly. So we print the configuration for the debug, and then launch each of the threads, and in those threads consists of forever loops, and they start running and start performing their functionality. So we have now seen that all the test bench components are instanced and they're started in the environment, right? So now next step is we want to move one level up and see where the environment itself gets instanced and used, right? So the way, like, the module is for the DUT, right? The program block is for test bench, right? So all the test bench environment tests are all instanced within the program block. Although when we come to the UVM methodology, we'll see that the program block is not really utilized, but from the SystemVerilog, due to some limitations, we'll talk about that. But program block is typically expected to instance all the tests and the environment. Every test bench code is expected to put into the program block because of the way program block gets scheduled in the scheduling semantics to prevent the race conditions, right? So we will talk about that a little bit ahead in the future sessions. But for now, we have this program block that we have declared called FIFO Testbench program, and we are passing the FIFO interface, right? So now if you remember, initially when we started off in our TB top, right, we had instanced a FIFO interface, we had connected it to the DUT, and that FIFO interface instance, we had passed it to the program block instance, right? So now this is the definition of that particular program block. So we take the FIFO instance that we are passing, and we are including the FIFO environment, and then we are including some whatever the test that we intend to implement, like a basic push pop test and a basic FIFO full test. So multiple tests we can implement. We are including those tests into the program block, and here we are declaring another variable called string. String is another scalar, is actually aggregated data type that is present in the SystemVerilog. It's actually array of characters, and we are declaring a test name, and we are instancing each of these tests, right? So we will see what are these tests. So tests are actually classes. We will see how they are implemented, but for now just understand that whatever the test that we have included, we have created an handle for each of the tests, and then we have this one initial block, and inside that we are first instancing our environment, right? So we have instanced our environment, and then if you remember, as a part of the Verilog refresher, we had looked at this system task called $value $+r. So what this does is, when I run the test, if I have passed on the command line plus test name equal to some string, whatever the string that is passed, that I can extract it within the test bench into this variable called test name. And if that is not, there's no name that is passed, then I will just set it to the basic. So if you can look at it as not over here, right? So if nothing has been passed, I'll set the test name to a basic push pop test, right? And once I've extracted the name that is passed on the command line, then I will come over here and check if the test name equal to whatever the test name that I intend to, like, that are available. Then if it matches this basic push pop test, then I will instance a test, right? I had already declared a handle over here. I'll instance a test, and I will pass the environment handle that I have. It's actually an environment object because I already knew it. So I will pass this environment object as a part of constructor to the test, right? And then I will call run to that particular test, right? And so now next we will see what is contained within each of these tests and what happens when we call the run for that particular test. So let's look at what's contained inside the test, right? So what happens is, every test will have some common steps and few specific tests that are intended to be performed only for that particular test, right? So it's always like this. So now what we want to do is, we don't want to code the common steps across, like I could be writing hundreds of tests and all the common steps that I perform across all the 100 tests, I don't want to keep on coding them again and again. I would like to reuse them. So how do we do that reuse is where the object orientation aspect of the SystemVerilog comes into play. So what we are doing is, let's look at it how to do that. So we are creating a class called base test, and in that we are declaring an environment handle, and this class has the constructor through which it is receiving the environment. If you remember, in the program block, whenever a test was instanced, we were passing the environment object to that particular test instantiation, right? And then we were calling the run. So in the run, what we are doing, we are calling the environment build, in which all the test bench components will get built. Environment.reset, we were waiting for the global reset to get deasserted. In the run, we were launching all the active components to start performing their intended functionality, and in the finish, we will wait for the intended scenario to complete. That is what we are doing right now. This particular functionality remains constant across all the tests. So what we will now do is, let's say when I now have to implement a specific test, let's say this basic push pop test, I am saying extends base test, right? What this line 10 does is that whatever is the functionality that is present in this base test now becomes a part of this basic push pop test, and this is called as inheritance, right? This concept is called inheritance. So with the extend, all the data and functionality present in the base class, which is also called as a parent, now becomes a part of extended class, which is also called as child class, right? So it inherits everything that the parent has, right? And now what we are going to do in this particular test is that we will create a FIFO config within the test, right? So if you remember, we had created a FIFO config within the environment as well. So now what we are going to do is, we are going to create a FIFO config within the test as well, and we will instance that particular FIFO config. And what we are doing is, we are overriding the count with some specific number, right? So in the environment, we are just randomizing it. Here we are overriding the count with a specific value, and then what we will do is we will say this dot environment dot FIFO config equal to FIFO config test, right? And this everything we are doing in the new of the test, right? So we have done it. So now what has happened is when we had done the new of the environment, the FIFO config default FIFO config was created over there, right? Now that default FIFO config is now overridden by the FIFO config that I have defined in the test, correct? Because I had in the when the environment was instanced, the FIFO config handle that is present over here on the line number 20, right? So whatever that I had instanced, the FIFO config handle would have a default object that's that of the environment. Now that object is overridden with the FIFO config test. So now what happens is when I start the run, which happens after constructing the test, when I do the build or when I start the run, it will use the new config that I have put it in the through the test, right? So now when this program calls the run, the sequence gets performed, and when the generators generate, now they generate according to the config that I have set through the test. So now here I have just set the count, but you can imagine that I can control any parameters that are present in the config and make sure that it creates the intended scenario that I wish for, right? So this is how you build the tests and create the scenarios of interest. This is in the basic form, but the concepts and the principles, they remain same. See, now we have completed everything, right? So we have looked at the program block which contained all the test bench code, and we looked at a test, and the test took the environment, it overrided the configuration, and it called all the phases of your build, reset, run and finish. It called everything. And now let's look at and we have individually looked at what each of these components are doing. I know during the first pass it might be hard to remember all the things that might have happened. You might have to do a second pass through this session to make sure all the concepts are clear. But let's attempt now once again to make sure we put everything together one final time to show you how all the things are working. So let's see. So what happens when we call the run? Let's look at that point of time, right? So the run will launch the run task of each of the active components. So the run will start the push gens run, and that will cause the push type of FIFO transaction of the count, whatever that is specified in the FIFO config, to get generated. So 5 push transactions will get generated, right? And then the generated transaction will be, so all 5 of them will not get generated at one shot. So it will be generated, the repeat loop within the gen push will run for 5 times. So every time through the loop, what it will do is it will generate one transaction and put it into gen to push driver mailbox, right? And then the FIFO push driver is actually waiting on gen to push driver mailbox with a blocking peak. Blocking means it is waiting, right? So when you call a peak, what happens is that particular thread waits there till it finds a transaction in the mailbox, right? Now the transaction coming into the mailbox will actually unblock the peak, that the block will get unblocked and it will move to the next line of execution. So the transaction data will now be driven on the push interface, right? On the virtual interface that's present through the Modport, right? The FIFO interface.push if Modport, which is a view as a push view of the interface, FIFO interface. Using the clocking block, it will start driving the interface, right? And after it drives the interface, what it will do, it will increment the push count, right? Now what the push monitor will do is it will be monitoring. This is also an active thread, and we had launched the run of the push monitor also in the environment run. So it would be waiting on the write enable to get asserted, and whenever the write enable gets asserted, it reports this push transaction to the scoreboard. And the FIFO scoreboard, what it will do, it will push that transaction into that SystemVerilog FIFO queue variable that we had declared. So it will push it over there. Next, what happens is the push count update in that FIFO state, right, will unblock the popgen, right? So popgen was waiting on this FIFO state push count minus pop count to be not equal to 0, right? So since the push count now became 1, this is not equal to 0. So now the pop gen will get activated, and the pop gen now will create a FIFO transaction, and the created FIFO transaction, it will push it into this gen to pop DRV mailbox, right? It will put it in that one. Now the pop driver is actually waiting on this gen to pop DRV mailbox with a blocking peak, right? And this transaction coming in will unblock the peak, right? And then whatever here, it doesn't really use the transaction data, but actually it pops an transaction out of your FIFO interface using the pop-if mod port, which is using the pop CB clocking block, which is a separate clocking block modeling the pop view of the interface, right? And after popping the data, what it will do, it will increment the pop count, right? And while this is happening, this is all happening in parallel, right? So pop monitor is still active, and because it has its own run thread, which we had launched it in the environment, this keeping track of threads, multiple threads, is a very important part of looking at any test benches. So we have many times emphasized, even during that Verilog refresher, that time and concurrency, this is the concept, is a very important concept, and many times many people fail to understand this, and it creates a lot of issues. So you have to understand, so when the fork, then all the threads are active at the same time, right? It's not the sequential execution, but all of them are working parallelly in tandem. So pop monitor is also active, and it is looking at the read enable assertion, and whenever the read enable assertion it sees, because of the pop driver popping a transaction from the pop or the read interface, it will report the pop transaction to the scoreboard. Now what the FIFO scoreboard will do is, it will take from the push transaction data that it had stored when the push had happened into the reference FIFO queue data type. It does the pop front from that particular data type and takes this actually reported pop transactions and compares the data between them, and then the data has to match, because we are expecting the data to come out in the same order, right? Yeah, so so far we have seen like in the environment what happened as a part of build, and then we have also seen what happened as a part of reset, and we have seen as a part of run what happened, how each of the generator generated and the drivers processed, monitors figured it out, passed it on to the scoreboard, everything we have seen. Now we had specified the count of 5. Now what we will see over here is, how does the finish of the environment works, right? What it does, right? So this is also end of test criteria. Here we are interested in establishing two things. One, that we have generated the stimulus, and second, all the expected responses from the DUT have showed up. So in this line number 89, what we are checking is, we are checking whether the push count present in the FIFO state is matching the operation count that we have specified in the FIFO config, right? So this FIFO operation count was set by the test, if you remember. So once this matches, what it means is that the expected number of push operations have been generated from the generator, right? So the next step, that is on the line number 90, we are checking the FIFO state push count is matching the FIFO state pop count, which means that all the responses from the DUT have showed up, right? So all the stimulus has been generated and all the expected response has been seen by the test bench, right? This is the fundamentals of any verification process, that you want to generate the stimulus and you want to check the response of DUT, right? And after that you allow a drain time, so that if there is any residue in the design due to the stimulus that we have generated, which was unintended, gets the time to show up, right? And if that shows up, the test bench components will have a chance to flag that as an error. After the drain time, we are ideally expected to check the error count. That part I have not shown over here to minimize the total amount of content that is shown over here. So we are expected to check the error count in the same way that we had done it in the counter test bench, right? And if the error count is non-zero, then we say that the test has completed and the test has passed. And if the error count is non-zero value, then we if the error count is 0, then we say that the test has passed, and if the error count is non-zero value, then we say the test has had a failures, right? And then we call the dollar finish SystemVerilog task call to end the simulation, right? So at this point we have done a complete walkthrough of your test program block environment and all the test bench components, and then we have also shown how they interact with each other, right? So this marks the end of the development phase. Next we will go to the regression phase. So in the regression phase, I think as we had discussed, we utilize a lot of scripts because there are a lot of repetitive work, and the scripts are generally stitched together with the help of makefile. So we use shell scripts and then Perl or Python scripts, and all of them are stitched together with the help of a makefile, right? So now let's look at how do we sort of compile this type of a test bench. I'm showing it with the QuestaSim, but I think the same concepts apply to both, like even if you do it with the either the VCS or even the Cadence tools, right? So any of the tools, I think the concepts sort of remain more or less the same. So what we are doing is in the makefile we are declaring 3 targets. There's a work target that will create a work library in which all the designs gets compiled, and then we have created an RTL target through which we compile the RTL, and then we have a TB target, and there we are compiling our TB. So in the TB target, what we are trying to do is we are specifying our test bench top, and we are providing an INC dir with the test bench directory. What this means is that whatever the files that are tick included in the test bench top, the simulator will look for them in this particular test bench directory to find them, and then it will compile all of them together in this work library. So when on the command line with this makefile, the directory in which this makefile is present, when you call make compile, then it will come to this particular target on the line 1. So it will first call this work target for which the vlib work will get created. Then it will call the RTL target, then where you compile all the Verilog files. Then it will call the TB target where it will compile the TB. So once you have compiled the test bench, then you start running the tests, and running a group of tests is what we call it as regression. So here I'm going to show you one single test. When we say a command line, generally we use this term command line or a command string to refer running one particular test, right? So here I am showing you one of the target, like let's say save WLF. So what we are doing is vsim, we are invoking the simulator, and then we are picking up work.FIFO top. This is the design top that we want to simulate. A work library can contain multiple tops, and we can pick and choose in the QuestaSim which top do we want to simulate, and then we are specifying the test name is equal to basic push pop test, right? So if you remember in the program block we were using the value plus args with the test underscore name to extract the string of the test name that is passed. So this is what we are passing it over here, and then minus do allows us to run a set of commands that are given to simulator. So we are saying we want the coverage database to be saved as a basic push pop test.ucdb. UCDB is this universal coverage database that has been defined by Accelera, and many simulators now support this. This is a standard coverage database format. And then we are saying that log all, like this log minus r space /* means log all the hierarchies that are present in the design for the waveform, that we can use it for any debugs. Then we say run all, right? So when we say run all, the test simulation starts, and it runs up to a point where either it hits a dollar finish or you have a $fatal which causes the exit of the simulation, right? And then we have this -l basic underscore push underscore pop underscore test.log. So in this log file, any of your $display statements that you would have included as a part of your test bench components, or even if the RTL contained any of those will all be printed to this particular log file. This is the simulation log file, right? There exists a compile log file when you do the compile, which should be checked for compile warnings or errors, and there exists a simulation log file which is separate from compile log file, where you contain the test specific messages. All right, it's present in that particular log file. And then we are specifying -WLF. -WLF is the waveform format for the Questa simulator, and we are specifying the test name.wlf. WLF is an extension used for the waveform files in Questa. And then if there are any other additional options, we are specifying those. So once we do that, if I launch a target make save WLF, then what this particular command line will do is it will run this basic push pop test, and my coverage database will be dumped in this basic push pop test.ucdb, and my log file will be created in this basic push pop test.log, and then my waveform will be created as a basic push pop test.wlf, right? So if you notice, typically this convention of using the test name itself for the coverage database file, simulation log files, and the simulation waveforms is utilized, right? So next step, we will look at if this particular test fails, how do we go about debugging them. And we also have another component to it. So this UCDB file that gets generated, so every test, so when we run multiple of these tests, each of the tests will generate a UCDB file, and for all passing tests, this is very important, so we should not include the coverage of failing tests, right? So you have to remember this. So for only the passing tests, we merge the UCDB command. There is a another, like the vsim and vlog, so we have another option through which we can merge all the UCDB files, and once we have merged all the UCDB files, we generate a merged coverage report that gives us the coverage metrics from the entire test suite. So that is for the past tests. So for the failed test, we have to go about doing the debug. Let's find out how to do that. So anytime a particular test fails, so you should always start off with the simulation log files, and there are actually guidelines as to how you should do logging from your different test bench components. We will discuss them further once we go into the advanced topics, as this is the basic one. We are not getting into deeper into those aspects. But the key idea over here is I have put a snapshot of a log file, simulation log file. Although this is a simple simulation log file where we are just generating 5 push pops and a few hundreds of lines of log are there, you can potentially read it from end to end, from beginning to the end. But there can be log files that consist of lakhs and lakhs of lines, and the log files could be in GBs, and it will take a long time to even just open them up, right? So log files are typically not expected to be end read to read. Instead, what is expected is that you need to extract, you need to ask some questions and extract information from the log file to understand what has happened. And this is especially very important because for constrained random tests, you don't know what exactly the stimulus the test has created. So you have to ask questions. So as a first step for this FIFO Testbench, I would like to know whether all of my push and pop were generated, right? And for the simplicity, I might just look at the messages that are printed by the scoreboard, and here if I see like a scoreboard data match, it is showing me expected and the actual values that it has found. And if I look at the count of them, there are 5, right? And that shows me that 5 of the operations have been generated for, and each of those 5 operations the expected and actual data has matched. So in this case, the test has passed. But even if the test has failed, you should look at the error message, and then you should start off from the point that whether the test has, like how far the test has progressed by looking at the stimulus that the test has generated, and then localize the area that, okay, that you have some theory that, okay, this is what has gone wrong, whether it has gone wrong at the push interface or that has gone wrong at the pop interface, and at during what time region it has gone wrong. You should identify that localization information, which you also call it as like a triaging, using the log file. So using the log files, you have to do 2 things. One, whether the issue is test bench issue or a DUT issue, right? You should try to figure that out to the extent possible. And second is you should have isolated it to few specific interfaces and a certain time duration, and see if you can root cause it using the simulation log files itself, because generation of the waveforms takes additional time, and they sometimes for a complex designs the waveforms can be very big in size as well. So that is what you are expected to find out as a part of the debug process using the simulation log files. So after you have localized the interfaces and set of time regions where things have gone wrong, you would want to open the waveforms, right? And if you are not able to localize using the log files, you should go for waveforms. So waveforms provide hierarchical access to signal level information. You could go to any RTL hierarchy and look at what has happened. And waveforms are of course very important source of debug information, but after simulation log files, especially for verification engineers, right? And at the test bench top, you would typically find all the interfaces. This is very useful for verification engineers, so you can add the whole interfaces one shot. See, this is the benefit that if it was a Verilog word, we had to go and pick all the individual signals to look at them, but here we can just drag and drop the interface, and we can look at how the activity is taking place within the interface. Then and then that makes it easy for us to, and these waveform files can be saved, so next time when the similar type of a failure takes place, you can just open it up and you will have all the required interfaces in. So the primary point is don't jump directly to the waves. First do the level of triaging from the simulation log files, and then make a practice of getting into the waves. And one point that I want you guys to notice in this waveform is this write enable is never continuously high, right? And there is a reason for this, and this is because of the way we have used the clocking blocks. So there will be one of the exercises where you will have to write the push drivers and the pop drivers such that this idle period that we have over here, it should be eliminated, right? So that will be the one exercise that you will be doing. So this is how you utilize the waveforms. So this concludes, right? So we have built successfully a FIFO test bench using SystemVerilog, and we went through the planning phase, we went through the development phase, and we briefly looked at what happens in the regression phase, how we compile, how we run tests, how we run multiple tests, how we can merge those databases, and when the test fails, how do we go about debugging them, right? So briefly, we got an overview of each of these phases. Now, if we ask ourselves a question that is this a perfect test bench, the answer is far from it, right? So there's several enhancements and improvements that can be done to this particular test bench, right? Like you yourself saw that, like we didn't have error count, for example, and then in the FIFO push and pop interface, there were bubbles, how to eliminate those bubbles, and then we can definitely improve upon the logging. So there are several such improvements are possible, and we can add more tests. And we, of course, we have not yet touched on assertions and functional coverage. Those are areas by themselves. So as this one is a bootstrapping course, I wanted you guys to understand the fundamental concepts and then add on the top of that to the assertions and functional coverage. So the basic idea of it is that you, as we have discussed at the beginning as well, that you should know a pattern, right? That when if someone asks you to build a test bench, you should have at least one pattern that's clearly present in your mind as to how you would go about it. And till you have come up with your own ideas or you have come up with better ideas, right, you should make sure that you know this pattern very well. When I say pattern, like what's a test, then the test bench top like environment, and within the environment all the layers that we talked about, the generators, and then your interface level translators, and how you instance and connect them together, how you phase them. All these fundamental concepts are very important, right? So you should understand these patterns very well and keep them in your mind, so that anytime you are asked either to build a test bench, or if you start looking at a particular test bench, then you'll have certain thought process as to how to do it, right? That is the key component of why we did this exercise. So you should and after this, what you should do is you should definitely look at that and look at the code and make sure that you gain certain level of comfort with it, right? And we will do some more improvements to this one as a part of exercises as well. And at last point that I want you guys to like reflect is, we have now done a Verilog based test bench and we have also done a SystemVerilog based test bench, right? And you should be able to see the differences. For example, how we did randomization in Verilog versus how we did randomization in SystemVerilog, and which is better, right? So you also think about it, and how we grouped all the signals in the interfaces and how we were able to reuse, and how the overall structure and how the interaction takes place. So all these aspects, right? So form, like, you think about it and form a bit of your own opinion as to is it becoming better, and if it is becoming better, how is it becoming better, right? So think about it. That's another important part of this session, right? So now that we have finished this session, so the next sessions, what we will do is, in this session we had looked at various SystemVerilog concepts very briefly. In next few sessions we will go deeper into each of those constructs, like for example data types, classes, constraints. Although we have not covered coverage and assertions, we will do that in the next sessions. We will do a deep dive, and the idea is we map it back, right? So what we have done through this session is, like in a big jigsaw puzzle, you now have seen all the pieces and how they sort of fit together. Now when we take out each of the pieces and look much deeper into the details of each of the pieces, now you have a reference as to where this particular piece fits in the puzzle and what does it do, right? That was the main idea. So think of this test bench pattern, try to remember these aspects, maybe go through multiple times through this session and go through the code to make sure that you have understood, and if you have any doubts or question, clarify it, because this is the foundation, right, on which we are now going to build things, right? So this is the foundation, or this is the thread which will hold all the individual constructs like a necklace. It will hold them together. So make sure that you have you have kind of, it has internalized in your brain. And now when we start the individual constructs, we will map it back. Like for example, when we start looking at interface, then we will think about like push interface, pop interfaces, and where it was fitting in the test bench, the virtual interface. All those concepts will, now we will go deeper into each one of them. When we look at the data types, we will definitely come across a queue data type. What are the different methods available with it? Classes, like how does the inheritance work? When we go more detail, I want you to remember that, okay, how we had applied the inheritance to reuse in terms of tests. So all these concepts that you have seen already, the real life applications of it, from the constructs from a language perspective, what are the further features provided, we will look into it. But whenever we look into it, I would request you to map it back to this test bench, because ultimately, as we have discussed before, the SystemVerilog is a domain specific language, and we need to understand the domain and every time map it back to the problems that we have seen in the domain, how we have applied. I understand there are various methods of doing it, but at least one method should be clear in your mind, and for every construct you should be able to map it back to one usage, right? I am not talking all possible, that you will learn as you experience, but for one usage it should be very clear, and I want this example to be that one usage that clearly sticks in your mind. Okay, so thank you everyone for listening. This was a long session, but I hope this lays the foundation, and we will build now each of the constructs further in next sessions.